Hello, everyone out there in Cyberland. We continue the Super Bee videos here. This one, we are all physically attracted to each other. Yes, indeed. I say that again. We are all physically attracted to each other, and not just us living things. We're attracted to me, to this computer screen, the chair I'm sitting in, my new fish, attracted to each one of them, and to the water in the tank, and so on and so forth, and to the moon and the stars and the sun above, whoop whoop, and all that ice out there that's keeping me out of school today. So we're all physically attracted. The story goes, Newton was sitting on the tree, the apple bonked him on the head, and he discovered gravity. Well, probably wasn't that simple or crazy, but somehow he noticed as this force, this gravity, pulled the apple to the earth, that as he looked in the sky, it must also pull the moon towards the earth. And perhaps the sun pulled the earth towards it, and so on and so forth. And he came up with this idea that anything that has mass attracts anything else that has mass. So, the big reveal, the formula, whoop whoop. Gravitational force is equal to big G, which is called the gravitational constant, times the mass of one body, times the mass of another body, over the distance between their centers squared. Whoop, whoop. An amazing concept, an amazing idea. And from this formula that Newton postulated probably around 1666, 7, around in that time, he figured out that you could figure out the mass of any other object in the universe by this formula. Then in one of my favorite experiments of all times, Henry Cavendish, a Englander, in 1798, after many years of figuring out how to do all this, his experiment looked something like this. And of course, I'm an excellent artist, so you can see here, he had two large lead spheres, balls, hanging from the ceiling. I think they weighed somewhere in the neighborhood of 80 pounds, maybe more than that. I don't remember exactly. And then positioned opposite to each one from another torsion bar right here, he had two smaller lead spheres also hanging from the ceiling. What he knew was the mass of each of these spheres, and he knew the distance between them, and he knew the force exerted by a little scale he had on the torsion bars here and here. Okay. You realize how hard it is to do that backwards on the screen. But anyway, you got that deal. So once he did all this, he did a little math, and he calculated G, which is the gravitational constant. That means it's constant. That means you can use it in this formula for any two masses in the universe, like Earth, Sun, Moon, etc. So in 1798, we were able to weigh the Earth. Even before we had discovered all the parts of the surface of the Earth, we already knew its mass. Let that sink in for a minute without putting it on a balance. We knew the Earth's mass because of Newton's basic idea of gravity, and that every mass exerts a force on every other mass, a gravitational force, a gravitational attraction. Now with that in mind, this is how we weighed or massed the Earth using this elegant formula. If you can see, there we go. So you say that weight, which is mass times gravity, is equal to gravitational constant times the mass of one object times the mass of another object divided by the distance between their centers squared. Now, the mass of us is inconsequential when we talk about the Earth, so we can cancel it out on both sides, which leaves us with G equals big G times mass 2, which is the Earth, over distance squared, which is basically the radius of the Earth. And if we switch those around, multiply by d squared, divide by big G, that is equal to m, which is the mass of the Earth. Then all we have to do is put in the numbers, and we can calculate the mass of the Earth like Henry Cavendish did in 1798. So you have 9.8 meters per second squared, as you remember, is acceleration due to gravity on Earth. Of course, on the moon, it's much less. It's 1/6. It's like 1.6 meters per second squared. And if we were wanting to figure out the mass of the moon, we could do the same thing with the different numbers, of course. So we have 9.8 meters per second squared, which is gravity, acceleration due to gravity, times the radius of the Earth, 6.4 times 10 to the 6 meters squared, divided by that wonderful constant that Henry Cavendish gave us, 6.67 times 10 to the minus 11 newtons times meters squared over kilograms squared. I'll get a screenshot of that. That is beautiful, isn't it? That math there. Okay. Page 2. Boop. There you go. So we got 4.01 times 10 to the 14th meters per second squared times meters squared over 6.67 times 10 to the minus 11. And we changed newtons to kilograms times meters per second squared times meters squared over kilograms squared. So the meters per second squared on the top cancels the meters per second squared on the bottom. Meters squared on the top cancel out meters squared on the bottom. And so then at kilograms on the top of the denominator there cancels out that kilograms per squared and gives you kilograms, which moves upstairs and gives you 6.02 times 10 to the 24th kilograms, the mass of the Earth. Thank you, Sir Isaac Newton. Thank you, Henry Cavendish. Part 2, I guess. And by the way, there is a question embedded in this video, which if you answer it and the 4 others that to follow, you'll get an extra point added to your midterm. And the question is, who was the person who came up with big G, who calculated big G? Go ahead, answer that one. And you can send that to me, email, along with the other 4 answers, and you got a point. Okay, part 2. Gravitational force is weight. Wait. People say in space people are weightless. Well, that's a bunch of baloney. People in space do have weight. Because if we look at this formula right here, gravitational force is equal to gravitational constant times mass 1 times mass 2 over distance squared. So in space, your distance from the center just increases slightly. So your weight only decreases a little bit, about the square of the distance, of course. And there's a picture in your book that kind of shows that on page, page 94, right there. So as you move away from the Earth, the gravity decreases by the square of the distance. So in space, your gravity may only be like 8.9 or something. That's still considerable gravitational force. So why do astronauts appear weightless, even though they obviously still have mass, obviously pulled towards the Earth with a gravitational force, which is slightly less than on Earth? So why do they feel weightless? Well, anybody know the answer to this? It's because as they go around the Earth in orbit, they are weightless because they are in constant free fall. They are in constant free fall. Kind of like that free fall after 30, 40 years of working on ladders. I was working on a greenhouse, and I was trying to adjust part of the roof on the top of this step ladder, and I forgot where I was, and somehow it slipped out from under me, and I took about a 6.5, 7 foot free fall. The free fall wasn't so bad, it was the landing. Ouch. Yes, so astronauts are in constant free fall. Like jumping out of a tree, you feel that moment when you lose your stomach, or when you on a roller coaster and you come down that first hill and you're almost free fall and you feel that sense of weightlessness. So that's why they appear weightless, is because they're in constant free fall as they orbit the Earth. So the other idea about this weight and weightlessness, or more weight or less weight, has to do with, like, when you ride an elevator. You may have noticed when you accelerate upward in an elevator, you feel slightly heavier. And when you accelerate downward, you feel slightly lighter. Well, the reason for that is, another picture in your book on the next page, I think 95, right there. There we go. As you move up, you feel gravity is increased slightly because of the pull of the elevator upward, and as you come down, the elevator car feels less weight. You feel less weight because you're moving downward. And if the cord were cut altogether, you would be in free fall and experience weightlessness altogether. And the free fall wouldn't be so bad. The landing would not be good, however. And you see there it said Farzad's story. I had a wonderful student once who's probably going to get the Nobel Prize someday, who is now studying, getting his PhD at the University of Minnesota. He had my class, and I told him this idea, as I told the rest of the class, and he was not quite convinced. So he got his mother, who was an English professor at Delta State, took her with a bathroom scale, and they went up and down the elevators recording the weight on the scale, and found out, sure enough, it was true. As they went down, the weight increased. As they went up, the weight decreased. And when they stopped, the weight was normal. Thank you very much. So the second question is, what was the name? What was the name? What was the name of the student who verified the idea of change in weight going up and down an elevator? Farzad, F-A-R-Z-A-D. Cool. This ends this first video. Hope you enjoyed. Tune in to you later, where we'll talk about projectile motion. Woo!